Hi everybody, Cal again with section 14.8, Lagrange multipliers. This is a short section, but one that takes a lot of concentration. This one, people find this one a little bit tough. But it's a really important method and is totally central in the subject of optimization, which I might add is one of the big research areas of our math department. And a really important field right now in a lot of jobs involving math optimization. So Lagrange multipliers is going to be important for a lot of people. I would go ahead and read the motivating paragraphs here on 981. And in particular, I would pay a lot of attention to figure 1. I would even suggest maybe going into your ebook and taking a good look at the little applet that goes along with this picture, so as to kind of figure out why Lagrange multipliers works. The upshot of this development is that if I want to maximize the value of f along this curve, g of x and y equals k, okay, I'm looking for a point where the level curves of f are parallel, are tangent to this curve, g of x and y equals k. Why is that? Well, let's kind of follow what's happening to values of this function as we're moving along g. Here, f is 7, f is 8, f is 9, f is increasing this whole time, and it stops increasing when this level curve, f of x and y equals 10, is just tangent to my curve, g of x and y equals k. And then my values of f start decreasing again. Okay? So we're looking for places where the two curves, g and the level curve for f, are tangent to each other. And the way we have to talk about that is by talking about the gradients of these two curves. If the two curves themselves are touching, are parallel at those points, then the gradient vectors, which are at right angles to the curves everywhere, are going to be pointing in the same direction. They're going to be multiples of each other. Okay? And it says this at the bottom of this paragraph here. At the point where f is maximized along g, the normal lines, the gradient vectors, are parallel. So the gradient of f is some multiple lambda of the gradient of g at that point. And this gives rise to the general method of Lagrange multipliers. If I'm trying to maximize a function f along a constraint, g of x and y equals k, then what I'm going to do is I'm going to set the gradient vectors to be multiples of each other. Gradient of f equals lambda times the gradient of g. Lambda itself is called a Lagrange multiplier, and this is one of your standard Greek letters, little lambda. And what I'm going to do is I'm going to use the method of Lagrange multipliers to find maximum minimum values of f subject to g. I set gradient of f equals lambda times the gradient of g. That gives me, if I have functions of 3 variables, this gives me 3 equations in 3 variables. And I need, in 4 variables rather, because we have x, y, z, and lambda. I need a 4th equation in those 4 variables, and the constraint equation itself, g of x, y, z equals k, gives it to me. So, we find all the solutions to these 4 equations, and we evaluate f at those points. Remember, we're trying to optimize f, and the largest value that I get is the maximum value of f, the smallest is the minimum value. So pay really, really close attention to this method of Lagrange multipliers. The rest of the section that we're going to cover is examples, and you want to pay very close attention to what's going on in examples 1, 2, 3, and 4. These are all really good examples of using Lagrange multipliers to optimize a function with respect to a constraint. I urge you to pay special attention to example 3, where we find extreme values of a function on a closed disk. And you can do the interior of the disk using the procedure from the previous section, 14.7. And for the boundary of the disk, you can use Lagrange multipliers. And so this is going to be an important idea for us. And example 4 is good too. Again, this is using Lagrange multipliers on a distance function. We are not explicitly going to cover the idea of 2 constraints. in this class, but for some of you who are going to be using this idea in other classes, in your lives, in your careers, it won't hurt you to know what happens when you're doing two constraints. And so I recommend that you give this section a read. I'm not going to ask you any questions about it, but that doesn't mean that it's bad info or anything. This is useful. And so I recommend that you do read this stuff. And if you're interested, then example 5 is a pretty good example. So that's the end of that section.